Today we're going to talk about algebraic expressions. These are instructions for a computation, and we'll learn about these by looking at several examples. First, let's look at 5x plus 7. Here, the letter x is called a variable, and you can think of this as a placeholder where you can put numbers in. You can pick any number you want and replace x with that number. And when you do the arithmetic, you get a new number, you get a computation. So we're going to do this for several numbers, and we're going to keep track of our work by creating a table. In the first column, we will put what number we put in for x, and in the second column, we will have what calculation we get. What is the output of our calculation? Let's begin with the number 1. In this expression, 5x plus 7, we're going to replace the letter x with the number 1. Now here you need to be careful. Look at 5x. What operation do we use? What is it, addition, subtraction, multiplication, or division? Well, in algebra, when you have a number next to a variable like this, and there's no operation in between, it's understood that you mean multiplication. So when we put 1 in for x, we get 5 times 1 plus 7, which equals 12. So in our table, when x is 1, the output is 12. Let's do another number. How about 2? When we replace x with 2, we get 5 times 2 plus 7, which equals 17. So when we input x, the output is 17. For our third example, let's plug in the number 0. Another term you'll hear is talking about evaluating this expression. So you can say, let's plug in 0 for x, or you can say, let's input 0 for x, or you might hear people say, let's evaluate this expression when x is 0, or let's evaluate this as 0. These all mean the same things. So when we plug in 0, we get 5 times 0 plus 7, which is equal to 7. Now, I don't want you to think you can only plug in 0 or positive whole numbers. You can plug in negative numbers as well. So let's extend our table and plug in -1 for x. So if we evaluate this expression for -1, we get 5 times -1 plus 7. Now, notice I put the -1 in parentheses. There's a reason for this. It's to avoid confusion. What if I had written 5 times -1 plus 7? I'm writing this diagonally because it's, I don't want this to go into your brain horizontally. Look at the first term here. We have two operations next to each other. We have the multiplication symbol and a negative symbol, and it looks like a subtraction. So it's very confusing. If you look at this, it looks like multiplication and subtraction right next to each other. So to avoid that, we're putting the -1 inside parentheses to let you know we're multiplying 5 with the number -1. Subtraction is not involved here. So 5 times -1 is -5 plus 7, which is equal to 2. So when we input -1, the output is 2. And we don't have to just plug in whole numbers. We can plug in fractions and other kinds of numbers as well. Let's input 1/2 for x and see what we get. So we have 5 times 1/2 plus 7. Now, when you're multiplying 5 and a half, remember, 5 is the same thing as 5 over 1, and 1/2 is just 1 divided by 2. So you multiply the tops and bottoms, that's how you multiply these fractions, and that gives us 5/2 plus 7. And if you compute this, you get 9.5. So when x is 1/2, the output of this expression is 9.5. So here we see how an expression works, and once again, it's like a numeric recipe. This expression is giving you instructions on what computation they want you to do. Let's see another example. Here, let's look at 3a squared minus 7a plus 1. A few things different here. One is we're not using the letter x for our variable. We're using the letter a in this case. That's fine. There's no law that says you have to use the letter x. That's just common. That's the most commonly used letter. But we're going to use a in this example. Once again, we're going to keep track of our work by creating a table over here where the input is a, and instead of using the word output, I'm going to use the word value. I just want to mix up the terms so you realize there's not one set of words you have to use to describe this process. So once again, look at the first two terms. 3a squared. Because there's no arithmetic symbol between the 3 and the a squared, it's understood that we mean multiplication. And the same here. We have -7a, so this is -7 times a. Like before, let's start off by plugging in 1 for a. That gives us 3 times 1 squared minus 7 times 1 plus 1. Now let's do the arithmetic. 3 times 1 squared is 3, minus 7 times 1 is minus 7, plus 1. When you combine these together, you get negative 3. So when a is 1, the value of this expression is negative 3. And instead of plugging in 2, we're going to jump over to 3. We're going to be a little crazy today. So now let's plug in 3 for a. We can also say, let's insert 3 for a, or let's evaluate this expression when a is 3. All these things mean the same thing. So we have 3 times 3 squared minus 7 times 3 plus 1. Let's go ahead and evaluate this now. Remember, exponents before multiplication, so that gives us 3 times 9, or 27, minus 21 plus 1. When you add and subtract these all together, you get 7. So when the input is 3, the output is 7. Let's do one last example with this algebraic expression. We're now going to plug in negative 2 for a. That gives us 3 times negative 2 squared minus 7 times negative 2 plus 1. 3 times negative 2 squared is 12. And negative 7 times negative 2 is positive 14 plus 1. Add these together and you get 27. So when a is negative 2, the value of the expression is 27. Let's see another example. In this example, we're going to introduce a few different things. 10 divided by x plus 3 times y. So here's our algebraic expression. What's different about this is this time we're actually dividing by the variable x, and then also we have two variables, not just one anymore. We have x and y. That means you can pick any number for x and any number for y, plug them into this algebraic expression, and see what you get. Although I'd like to say that there's one number that's a little bit forbidden, and we'll see that. So we're going to make a table here of our work, and remember, you can pick a number for x, you can pick a number for y, and then once you do the computation, you get an output. Let's start with 1 for x and 2 for y. If we insert that into the expression, we get 10 divided by 1, because you put 1 in for x, plus 3 times 2, or 16. So for this expression, this is an algebraic expression with two variables, x and y. When you insert 1 for x, 2 for y, and evaluate, you get an output of 16. Next, let's plug in 2 for x and 1 for y. That gives us 10 divided by 2, because we're plugging 2 in for x, plus 3 times 1, because we're plugging 1 in for y. This gives us 5 plus 3, which is equal to 8. So when we input 2 and 1, the output, or the value we get from this expression, is 8. One last thing. Let's plug in 0 for x and 4 for y. That gives us 10 divided by 0 plus 3 times 4. So what do we get when we evaluate this expression, when we do the computation? Well, if you try to do this arithmetic, you run into a roadblock because we have 10 divided by 0. Division by 0 is undefined, so this calculation is undefined. Let's now see a fancier example. Here, our expression is 17,000. So what do you do with this calculation? Well, first of all, there's no variables, so you can't plug any number into it. It's just 17,000. This is just a number. It's sitting there. So I wouldn't call this an algebraic expression. It's just a number, a whole number. It's a nice looking number, but there's not much we can do with it. We can't evaluate this for anything. It's just kind of sitting there. Let's jump to the final example. X divided by y plus the square root of z. Here, we have three variables, x, y, and z, so we can pick any three numbers we want and then plug them into this expression. However, remember, we can't plug in 0 for y because we'd get division by 0. Once again, we're going to keep a table of our work, x, y, z, and what value we get. To begin, let's plug in 1 for x, 2 for y, and 3 for z. And let's see what we get. Well, we replace x with 1, we replace y with 2, and we replace z with 3. So we get 1/2 plus the square root of 3. Here there's several things you can do. You could just leave it like this, or you could use a calculator or a computer to do the computation, and what you would get is 2.232, etc. The number continues forever, but this is a really good approximation. So the value is 2.232. And let's do one final calculation. Here, we're going to plug in 4 for x, 3 for y, and -1 for z. If we input these numbers, we get 4 divided by 3 plus the square root of -1. Now, there's a rumor going around that some young students have heard that you can't take the square root of a negative number. You can, you totally can. It's just the result you're going to get is a complex number. So here we get 4/3 plus, and the square root of -1 is a number called I. This is an imaginary number. So here, when you have a value involving I, we call that a complex number. So for this algebraic expression, when you plug in 4 for x, 3 for y, and -1 for z, we get 4/3 plus I. So to recap, let's quickly flip through all the algebraic expressions we looked at. The first one was 5x plus 7. It just simply said perform the calculation 5 times whatever number you want plus 7. The second expression we looked at was 3a squared minus 7a plus 1. Here the variable was a, it doesn't matter which letter we use, and this recipe was take 3 times whatever number you want squared minus 7 times that number plus 1. The third example introduced us to something important. You're not restricted to one variable. You can have 2 or more variables. Here we have 2 variables, x and y. And here it says pick any 2 numbers you want. Replace all the x's with one number and all the y's with the second number. And then we had this goofy example of 17,000. It's just a number. There's no variable, so you can't plug anything into it. And lastly, we had x divided by y plus the square root of z. And here, what I wanted you to take away was that there are 3 variables in this case, x, y, and z. And it's okay if the output is not a whole number or a fraction. It can even be a complex number. That's a number involving I, the square root of -1.